Okay, we now move into our flagship session with IonQ. IonQ is one of the most recognized names in commercial quantum computing, pioneering vertically integrated quantum systems and demonstrating real-world quantum applications. Today's sessions will briefly introduce quantum computing compared to classical computation, followed by IonQ discussing how quantum technology is moving from experimental advantage to scalable deployment across industries, spanning land, sea, air, and space via quantum networking, quantum sensing, and quantum infrastructure. Please welcome Daniel Pompa, quantum field engineer from IonQ. Thank you.
So what I'm going to do today, let's see if this will progress this way. Okay, I want to first talk about our quantum computing. I'm going to talk about it in two different terms, one in hardware, so sort of what the hardware is, how it works, and then talk about some of the applications that we are pursuing, so you can all get a better sense of like the broader scope of what quantum computers will be capable of, and get maybe a better sense also of like the sort of timelines that we're thinking about with some of these things. I'm also going to talk a little bit towards the end about security and networking and what we're doing in sensing and ultimately space infrastructure, but I wanted the bulk of this talk to be more focused on the quantum computing aspects, because we see that as being sort of like the holy grail, if you will, of all these technologies. And ultimately, we'll see these technologies converge in applications that are, you can think of as like an integrated platform approach, and I'll get to that a little bit. So just jumping in, we are, as a company, the goal, so as David mentioned, Dr. Chris Monroe, Dr. Jungsang Kim founded IonQ back in 2015. And since its inception, the plan was always to build data center ready quantum computers that can be photonically interconnected, so we can actually have distributed computing systems in the same sense that we have distributed computing systems classically for like high performance computing centers, right? So we really wanted to get away from technology in a lab, right, that is like controlled and run by graduate students and postdocs and really smart professors, to more portable technology that can sit inside of a data center reliably, robustly, over long durations of times, and interface with the classical high-performance compute hardware that is already there. And for that, we are now building our 5th and 6th generation systems. So we've been doing this for a while. Okay, so earlier systems looked more like a lab, right? It was like a lab in a box. But what we're getting to now with these later systems, so the 5th generation system we're building now, we're going to start shipping these out. We have one going to KISTI in South Korea that's going to go sit in their data center with minimum environmental requirements. The way that we design these systems, you know, if you're familiar with quantum computers, you might know that they're sort of vulnerable to their environments, right? And there's lots of ways that the environment can interact with those systems and kind of mess up the computations. So what we do is we actually try to mitigate all those things inside of these boxes, right? So we have like a vibrational table with hydraulics to help to mitigate, you know, any vibrations in the ground, that sort of thing. We try to self-contain all of those mitigations within these boxes so that we can deploy, again, with minimal ask of the environment that we're deploying it into. So we have that system going out to a number of places. It'll be a 100-qubit system. The following systems, and then from this point on, we'll be transitioning to a new architecture, and I'll explain what that architecture looks like in a moment and why we're making this transition. But we believe that this transition will allow us to scale, and scale very rapidly. Actually more rapidly than any of the other kinds of quantum computers are projecting to do to date. So I'm going to show you some of that. I'm going to make some justification for why, and hopefully by the end of this talk you'll all believe me. Okay? All right, so before I get into that, I want to start with, for those of you here that are not as familiar with quantum computers, you know a little bit about classical computing maybe, my plan is to help everyone get to a point where you have some intuition for how these devices work, and you have a clear reference and comparison to what's being done classically. So classically, back in 1945, this mathematician, computer scientist, John von Neumann, and some others worked out some of the original schemes for how we build our classical computers. Today it's called the von Neumann architecture. And I won't belabor this and go into all the details about how this works, just to give you a sense of how we make this transition. It's effectively you have some input that you take into some central processing unit. That central processing unit will do some logic operations. And computer scientists have got really good at understanding how you can take fundamental logical operations, right, just true-false scenarios in so many sequences and configurations, and then get some really robust, detailed calculations and outputs from those systems. So that's where we started with, and even in those days, von Neumann is one of the most brilliant mathematicians and computer scientists. He already had the foresight that I believe is kind of pointing to this transition that we're making now from classical to quantum computing, where he said that ultimately this technology is going to get away from this era of problems in intensity, substance, energy. And I think about this as like the high-performance computers that we're building today that, we're talking about the amount of power consumption that you need to power these AIs that we're all adopting all over. And we start to get more methodical into like structures, organizations, and how are we the most efficient that we can be with the information that we have. And I believe that quantum computers are really a great asset for that. Efficient processing of information. So at the basic level, it looks something like this. These logic operations really just work off these fundamental components called transistors. You can think of transistors as being like these A and Bs in this scenario. And they're really, I want you all to just think about it for the sake of this talk as them being like switches. They're like on and off switches, 1 or 0. Right? And I can put them together in all different kinds of configurations, and I can just do basic logic with them. I can say, okay, if they're both on, then make the next one be on. If they're both off, make the next one be off, and so on and so forth. This is the construction of what happens within that central processing unit. This is classical computing. Now, these transistors they come in many different varieties. They're very simple. We've managed to make them very, very small, right? This is the Moore's law that everyone hears about, where we managed to make them smaller and smaller and smaller and fit billions into like our phones and our computers. But that's sort of starting to seem like it's going to taper off. There's really only so many gains that we can continue to get of just making these things smaller and smaller before we start to hit the fundamental physical limits of these systems, where we get closer to the size of the quantum realm, where quantum mechanics dictates their interactions. So I like this. Helen Keller famously said, "Alone we can do so little, together we can do so much." Here, clearly, the transistors agree with this. This is them saying the same thing in binary. And so just to get a little bit of intuition around this thing, a transistor, like I said, you can think about it as being like a switch. I can have it in an on state. I can have it in an off state. I can't have it in between, right? It can only be one or the other, right? But with the quantum computers, I can. So I know this is a bit more complicated. Some of you may be familiar with this. It's called a Bloch sphere. This is the conceptual diagram for a qubit, the quantum bits that we use. And you can see here that at the top we have what we'll call the off state. At the bottom we have what we'll call the on state. And we can actually put sort of toggle some sort of knob control to where that state can be anywhere as like a vector on this sphere, right? So we get a lot more robust ability to control and maintain information. And the way that it works is roughly something like this, so bear with me, is we have, say, a linear combination. So we are combining both of these potential states, and each of that off state, the ket 0, on state, the ket 1, they have some probabilities, right? So there's some probability that it's going to be in the 0 state, some probability it's going to be in the 1 state, and we can control that. We can try to influence it in such a way that we get it to be a 0 when we want it to be, we get it to be a 1 when we want it to be, if that makes sense. Okay, So the way that we actually program these things, it's a lot like a musical stanza. So you can think about this as, this is a quantum circuit. These are those same types of logic operations that I was mentioning in the classical analog, right? Here we just have a register of our qubits that's described as the width of the circuit. So the more qubits you have, the wider circuit. And then we have the numbers of operations that we can execute on our quantum circuit, right? And that's the depth, right? And that's really what we want to do. We want to go as wide as we can and as deep as we can so we can do all the calculations we project will make all these great advances that we claim. I won't belabor all of this, all what each of these do. What I want to do is hone in on one specifically here, is just this piece of this circuit. I will say real quickly that there are some dynamics that are unique to quantum computers. They need to be reversible. So anything I do, you need to be able to go backwards, right? Because these are physical things and you can't defy the laws of physics. But they are dynamic. So I can do an operation, and with some of our quantum computers, we can reset those qubits that we have and reintroduce them and do conditional logic. So the same kinds of ways that you program classical computers, we'll be able to program quantum computers, all with a different medium of how we can store and manipulate information, if that makes sense. There are some caveats. We can't clone these states. So that's an important thing to keep in mind as we talk about, things like error correction and things about trying to get to like fault-tolerant quantum computers. Okay, for that chunk of that circuit, this is considered like the hello world of quantum computing. So if any of you want to go get on, say, like an IonQ computer, you can right now, right? So we're available through all the major clouds, Google, Microsoft, AWS. You can go run this right now. You can construct this very simple circuit, and you will effectively be able to create what's called a Bell state. This is an entanglement of your qubits. What entanglement means, and I'll try to make this a little bit more clear in a moment with an analogy, is that the qubits now have a shared state, and it is inseparable. Anything I do with one, I am having some effect on the other, right? And to make this a little bit more clear, a little bit more intuitive, I think of this sort of like if I had two yarn balls, right? And then if I was to take my yarn balls and put them together and interweave them in such a way that there's really no way that I'm going to like separate them now without having some effect on the other, right? They become this combined singular state. So anything that I do to one, I'm like inherently doing something to the other, if that makes sense. Okay? Now the last principle that I want to mention here is interference. So we have superposition that allows us to be in this in-between state of 0 and 1. We have entanglement that allows us to have shared states between these qubits. And then we have something called interference. Interference basically describes something like this. I have my qubit. Qubits quantum mechanically are represented by something called a wave function. You can really think about this as like those probabilities of the zeros and ones and stuff that I talked about are kind of like the peaks on these waves, right? And I get to manipulate those peaks. And I can try to control the height of that peak that corresponds to the probability that I get that particular state of the broader set of states that I can get. And interference allows me to try to decrease the probability of some states, increase the probability of others, so I get the state that I want. Does that make sense? Okay, so that's a really powerful tool because in quantum computing, I'm getting to work in this massively larger state space, but I need to be able to narrow down to the actual solution that I'm trying to find. And this is a key capability that allows me to do that. Okay, so I'm going to do this just a little bit longer to build this like last little bit of intuition before I go into what IonQ is specifically doing. So with the transistors, you think about it like a light switch, right? It's just on or off. And I'm happy. In the ideal world, my light bulb always works just as I want it to, and I can turn it on, I can turn it off. It's deterministic. It does exactly what I expect it to. In the case of quantum computing, I like the analogy of thinking about it kind of like a dimmer switch. And quantum mechanics is a little weird, so I'm going to add a little bit of extra layers to this. So what I'm trying to depict here is actually more like I have a 5-year-old daughter, right? And I put my 5-year-old daughter in her room, and I close the door, right? I can't see what she's doing in there, but I can tell her what to do. If she does it, I don't know until I open the door, right? I hope she does what I say that she's going to do. She's 5, so, not always exactly what I might expect. But I can give her instructions. I can tell her what to do with this dimmer switch that she has. And I can give her an instruction like this. So with the Q bit, I say, that's ket 1, turn the light on, it's fully on. Okay? I can give her the instruction to turn it off, it's fully off. Again, I don't know until I enter the room actually what the state is. And because quantum computing is probabilistic, I really have to kind of enter the room many times to get confidence in the state of where it's at. And maybe this will make it a little bit more clear. You remember in that circuit that I showed you earlier, there's this H gate. This is just one of the many operations, but this H gate in particular will put my quantum state in this halfway point, right, where it's kind of 50% on, 50% off, right? What that translates to probabilistically is if I am outside of the room and I open the door 100 times. 50 times it's going to be maybe my daughter gets startled and flips it on. 50 times maybe she gets startled and flips it off, right? There's some probability of the different states that it's going to be in, and this is that perfect superposition where half the time I can expect it to be one way, half the time I can expect it to be the other way. There are also additional degrees of freedom here, though. Because I can rotate around this axis, I have the control over what's called the phase of the qubits. It's an additional degree of freedom. It actually has nothing to do with color. I just use this as an analogy to give you some sense, because the color here, or the phase here, doesn't change the likelihood that that vector, that state, is going to flip to 0 or 1. It has no effect on that. It just alters this 1 degree of freedom. But that shows you we have this additional degree, this other dimension where we get to kind of encode some data, some information. Okay? All right. So with qubits, I can have many more qubits, and I can put them in their own individual states. They can all be in the same state, some halfway point state, like what I showed a moment ago. I can also have them in all kinds of different configurations simultaneously. And I get access to all of these different configurations simultaneously. And what's really interesting about that then is if I go back and compare to the transistors that I was talking about a moment ago, the qubits that I can have far less to represent the same amount of information. So if I have 35 transistors that are just these 0, 1 switches, I can represent that with something like 6 qubits, okay? So that may not seem that significant to any of you. It's like 35, 6, who cares? Like, that's not that big of a difference. And we have billions of transistors, right? So again, who cares? So what's interesting about this is the constraints of the transistor systems versus the constraints of these qubit systems, right? In the case of the transistors, you can have up to this exponential number of configurations of ways you can turn different ones on and off, right? But you can only actually access like one set of those at any point in time, right? So it's really like if you have a 1 bit, you only have like 2 bits classically with the transistors, and you're really only doubling here, right? So if I have 1 bit, then I have 2 classical states. 10, I have 20, and it just goes on just doubling in this way. Quantum, it grows exponentially because I have access to all of the states all at the same time, right? So you can see how this scales very rapidly, and this is interesting. So at 1, I still just have 2, but at 10, I have already over 1,000. At 100, I have this massive number, 10 to the 30. So to give some people a sense of that, a billion is like 10 to the 9, a trillion is like 10 to the 12. This is already a massive number that most people don't know the name of it, right? At 256 plus, roughly, I get close to the numbers of atoms estimated in the known universe, right? That's a very significant amount of computational space and information that I'm getting to unlock with a fairly modest number of qubits. And this is where things get really interesting, is our roadmap. Is there any way to dim these lights? Can everyone see this? Okay. Our roadmap projects that this year we're building that 256 qubit system. So we're already about to have that system, and we're already going to be exploring what that means, what we can do with it, with some ideas of what we've done with the smaller scale systems. But the expansion of that growing to larger systems is rapid because of this new technology, and I'll explain how our core technology works in a moment. But it scales very quickly, right? We grow to 10,000, we build systems at 10,000 roughly next year, roughly the year after that, we double it, and then it goes up by a factor of 10, and again by a factor of 10. So by the end of the decade, we're projecting to have systems that have millions of qubits, right? And we're constantly trying to bring these numbers in. We mentioned that we're trying to acquire SkyWater. SkyWater is a foundry that specializes in making the chips that we're designing, I'm about to talk about. And if we can bring them in, then we can bring those things closer. So this is a very exciting time. These numbers start to grow to massive things that we can't comprehend. So then the question becomes, well, okay, what are these computers actually useful for? Okay, so before I get into that, there are a number of ways to make quantum computers. It's really like, can you construct a qubit? Can you make that state? Can that state be manipulated in all the different ways that I mentioned before to get these properties, right? Can I do it reliably? And then what are the trade-offs with the different approaches that you take? We like trapped ions, but like I said, you can do these with electrical circuits to make synthetic qubits. You can do it with neutral atoms. Trapped ions and neutral atoms are natural qubits, so we just get them from nature. They're all perfectly identical, so it's nice to get to work with those. And you can do it with photons. You can do it with molecules. You can do it with spins in condensed matter systems. You can do it a lot of different ways. We like trapped ions, and hopefully this will make sense as to why. So we acquired a company called Oxford Ionics. Oxford Ionics sits at right near Oxford University. A lot of their researchers and actual leaders at the company came out of Oxford University, and they are absolute leaders in this space, besides Chris Monroe and some of those folks on that side of the pond, in how do you trap and do computational controls on trapped ions to construct something like a quantum computer. Now we realize that we really need to ideally be able to move our ions around to do computation. There's a lot of reasons to do that. It really opens up the dynamics of what we can do when we program these things. So we now have this ability. We can move our ions around on this chip because ions they're ionized atoms, so we can have these electrodes, DC electrodes that we vary the voltages, and that kind of pushes the ions around. So we have that control. What's unique about this compared to other trapped ion companies is we're really getting away from computational laser controls, right? This is really the reason why we're going to be able to scale to these massive numbers and why some of these other folks are probably going to struggle with it, because it's really hard to scale up certain types of lasers, and the lasers that you need for trapped ions are very finicky and cumbersome, and it takes a lot of fine-tuning control. So what we do here is we have an antenna, propagates a magnetic field, and that's how we do all of our computation. But, and one last thing and I'll move on, what we're showing here is that we can build our chips as one integrated stack, and then we can manufacture these, we can process them with traditional semiconductor manufacturing. So we can print these things out on wafers, right? And we're already doing that. So the 256 systems, we already did tape out. We're already printing these things out. And now we just need to demonstrate that they will keep up in the level of performance that we've shown at this 2-qubit unit level. So we have smaller systems where Oxford Ionics IonQ has now demonstrated the leading fidelities in the world. So these are world records for the things that matter most for quantum computers. So how good do they actually do the operations that you want them to do, and how reliably can they do that, right? So 2-qubit gate fidelities, like those entanglement fidelity, or those entanglement gates that I showed you earlier, that's the leading contributor to error, right? The more of those you do, the more likely your computation's not gonna go well. So this translates to roughly something like, 1 in 10,000 of these gates will fail, right? And we want to get that number lower and lower and lower, but we are right now holding the record. We also hold the record for 1-qubit fidelities and state and state preparation and measurement operations. So that's the plan. We now know that we have this unit cell. We can scale it out, right? We know how we can sort of just start to tile these things together. Since all of our computation is dictated by these underlying antennae, the antennae are just connected by like a global AC current line. And that global AC current line can sort of meander across this chip, hitting multiple unit cell layers. So with the 256 system, we're going to demonstrate this technology, get everything out of it, show how we can do error correction. But then what we want to do after that is we want to start to tile these things together. And it really just becomes an engineering challenge at this point. We don't need to do new physics. We understand the physics very well. Okay? All we need to do is efficiently engineer these chips, tile them together, and we could potentially go up to numbers even higher than 10,000 qubits on a single chip. Okay? All right. So I know what a lot of you may be wondering. Get to the point. What can we do with these quantum computers? So initially, when people were first dreaming about quantum computers, there were only a few things that they came out with that, there was a couple algorithms that looked promising, and then a lot of algorithms would come out, and people would be like, oh, no, that doesn't actually work. So what we've done is we've tried to narrow down, while keeping broad in all the different potential areas for applications. And we're seeing still that quantum computers will influence all these major industries, right? And we're still not fully appreciating all the different industries that we can apply these devices to, but we are getting a sense of the types of problems that we can solve, right? And we're getting a sense of the types of algorithms, and the algorithms that we know that we verify the computational complexity, if you will, and then show that as we get to a large enough quantum computer, we'll execute this, we'll do better than what you could do with any of these high-performance classical compute resources. And how have we done that? Well, we work really closely with partners. We work closely with academics at universities. We work closely with researchers at national labs, top researchers at commercial industry companies that have the problems that we need. They understand the problem space well, and what we want to do is try to address the problems that we have with the resources that we have today. So all of these projects that we're doing now are with smaller system sizes that, again, are all available of something like 36 qubits. But we're already, just with 36 physical qubits, starting to see some indications of advantage beyond classical. And I'll give you an example. With AstraZeneca came to us. They wanted to analyze a drug development process where they say, we use this really expensive material, these molecules, for something called catalysis, and we want to see what happens when we use a cheaper catalyst, a cheaper kind of molecule in that process. But doing all that in a wet lab's really expensive, right? So we really like to simulate everything computationally first so we get a sense of how it works, and then we'll actually invest all these dollars into exploring it in a wet lab. So what we did is we actually used our quantum computers to help them in that process and showed that compared to the next best state-of-the-art solutions available to AstraZeneca, we got a 20x improvement in the full workflow. And that's how these things work. It's not just like a quantum computer comes in and replaces everything the classical computer does. They work together, and the more closely together they work, the better. Okay, so we're doing that in simulation software with ANSYS and also finding gains there. It's narrow now, but we project that we'll find a lot more significant gains as we build out these systems. Okay, so the next part of this talk is probably going to be the most technical, but I wanted to give everyone an example of one of the algorithms that we're interested in and that maybe some of you haven't heard about as much. So this is something called topological data analysis. This is the research that I'm interested in. I work with our researchers to try to explore this topic. I think it's fascinating. The areas of applications seem to be ubiquitous. So this is potentially applicable across chemistry, brain health, robotics, finance, you name it. And the reason being is it's just analyzing data. Right? And the data, the type of data, doesn't really matter as much as you can construct it as these graphs that we use, right? So we can take in all kinds of different sorts of input data. We can kind of lay it out as these graphs that we want to analyze, right? And then we can start to look at things. Topology has to do with this concept of like things that persist over time. So if I have something in that data set and I manipulate my data, that thing seems to persist. And maybe the fact that it persists, maybe that tells me something and I want to know about it. Maybe I can feed it to a machine learning model and it will tell me something even more detailed. So the quantum comparison for something like this, so I'll step back. Topological data analysis works off constructing these types of graphs. They're called complexes. But the simple construction is I take increasingly higher order dimensional objects and I analyze those to see if they have this sort of characteristic of being what we call like a hole in the data set. That's that thing that persists over time, and maybe if these holes are there and we can find them and we can understand them, it tells us something deep about the data and we get to probe in deeper or again feed it to AI and see if it can help us there. As we scale this out, classically, we very quickly hit a wall. Because of the types of mathematical calculations that you have to do classically, it becomes very quickly intractable, right? You can really, depending on the size of the amount of data that you have, you really only go up to things like this tetrahedra, sort of like three-dimensional kinds of shapes at best. And even if you're doing that, it's going to be really slow and take a really long time if the data set's big. But what's interesting is there's might be something informative in data sets that are much higher dimensional, and that's where this quantum algorithm comes in. So we start to see, and it's been shown, that for certain types of graphs, we call them like k-partite graphs, we could potentially get an exponential speed up for our quantum algorithm versus the classical, right? That's huge. It's a massive difference, taking something that couldn't otherwise be done, now doing it on our quantum computer, and now getting to probe data sets that we otherwise couldn't get this kind of information out of it. So what's an example of this? One example is the human connectome. So the neuronal structures in your brain are very complex. You have billions of neurons, right? And they're all interacting in this convoluted, kind of complex ways. And to this day, neuroscientists still struggle with trying to take all that brain activity, right, and try to understand how does that build up to the point of like our cognition and our metacognition, and how can we learn from that? So what we did in our study is we're looking at, can we do something like take fMRI brain signal data, can we construct this kind of graph so we can analyze these systems, and can we do something as simple as like try to predict Alzheimer's, right? Is there something about the configuration of all these interconnected points in the brain and some of those persistent features that I mentioned earlier, can I take all that, feed it to a machine learning model, and can it better predict Alzheimer's? And we're already starting to get really interesting results from that. And what we're really doing is we're trying to build out these pipelines. So like I said, quantum computing works in this hybrid approach, where you're doing it alongside classical computing, and you're trying to get the best of all the resources that you have. So what we're doing here then is we're saying, okay, on the quantum side, we'll take the data and we'll do all this processing, right? We'll extract these things, these holes, as some kind of feature vector, and then that feature vector, if you're familiar with machine learning at all in AI, it's just another feature vector that you're going to put alongside all these other features that your AI model will evaluate, and it'll get better or worse at trying to predict some outcome based on the data that you give it. Now what we're seeing is when we do this process with the quantum computer involved, that we are going to get, in many cases, higher accuracies for the models that we are using, because we're giving them a bit of information that they otherwise couldn't have got hold of, right? So another good example of this is in financial data. So we did this study with financial time series data, and what we've shown is that we can extract any kind of time series data that has a lot of different complexity, a lot of different things that are influencing why say that stock is moving the way that it is. And if you're familiar with the stock market, you kind of know what I'm getting at here. We can extract that data as a point cloud, and we can do the same kind of thing. We can say, can I learn something from this data that tells me about maybe something that's going to happen to the stock? So what we found was that, you remember how I mentioned that these different dimensional holes might tell you different things, and the quantum computers really get good at around like these H2, like 3D holes and 4D and beyond, is that these higher dimensional voids, these holes, are giving stronger signals for extreme events in the stock market, right? So now we're wondering, okay, is this a more like reliable or useful tool to try to analyze stocks or any kind of time series data or signal processing? There's lots of things that we can start to think about doing with this, and we may not understand all the nuances of what these voids are doing or what they mean. We don't necessarily have to. We can just look at the results that we get. Okay, so, and I'll close this out with this, we are doing projections for where we think we'll reach that advantage for quantum versus classical, right? And what you see here in this graph is what we are saying is the Beatty is like the dimension of the hole, if you will, and then we compare the dashed lines as what the classical can do, and then the solid lines is what our quantum computer will do. And you see, even at pretty modest numbers of qubits, so these are devices that we're going to have, like now, we're doing these tests now, that will be able to reach these crossover points from quantum compared to classical and be able to demonstrate clear quantum advantage. And as we scale these things out, those dimensional holes will reach that advantage at even lower dimensional holes and be able to spread this over all different kinds of applications. Okay, so I did want to mention also, while I have some time, the other things that we're doing. We have put significant investment into quantum networking and quantum security. There's a lot of reasons to do this. The obvious ones from the security standpoint is that we believe that we have now methods to make more secure communications in our networks, right? And there's a couple different ways that we can do this, and I won't belabor this too much, but we have physical boxes that can do this now, and we have physical networks that we've deployed that are doing this now. So this isn't just like a future technology. This is an existent technology that is getting deployed all over the world, okay? So one way that we can do this is from our acquisition of Qubit, they showed that they can do entangled photon sources and do what's called quantum key distribution using those entangled photons. And remember when I said like you entangle two, what we call like the photons are like qubits in this state. If you entangle them together, you can separate the physical qubits at a distance, but they share the same state. I could take a qubit and keep it right here and send the other to the Andromeda galaxy, and if I do something to this one, it has a direct effect on this one. Or at least, if I know what this one looks like, I'll know what this one looks like definitively, right? So I have that as an option, and then I also have other protocols that I can use that allow me to track if a sender sends us a signal to some receiver, they can verify the state of the qubit that they have on the other side, or the state of the system that they're working with on the other side. So we have these boxes, they're deployed. One example of this is we have what's called a Bohr-4 network sitting in Chattanooga, Tennessee. This is a really nice testbed framework for actually exploring this technology. We're not just doing QKD with these systems. It's really a platform to allow people to come in, and the company that we work with, EPB, is the utility provider out there. They're actually bringing in commercial customers to test these things. They're bringing in real dollars to test on this system and see, how quantum key distribution works, or how these electronic equipment that they want to use for their experiments or ultimately their deployments will work within this infrastructure, and we can help them do that. And then it's also helping us kind of take our first step into the next layer of things where we're deploying a quantum computer. Ultimately, what we want to do is build distributed quantum computers that are connected to these metropolitan networks that are connected at longer distances to build wider networks that span the globe. Because what we really want to do is build what's effectively like a quantum internet. Okay? We're also working on these quantum sensing systems. So this is, as David was mentioning, this is all about position, navigation, timing. We have the world's most precise deployable atomic clocks. I think that's an important point to make here. So the most precise atomic clocks in the world are labs, right? There's some lab sitting off with this very convoluted contraption that they put together that's maintained by some postdocs and graduate students, and it, has high likelihood that it's going to go down. It's not reliable, but it's static. It's just sitting there. The next best thing is there's companies that put that in a box, right? And they still get really good performance, not quite as good as the lab, but it's more reliable, and they can go and take that box and put it somewhere. But that box still needs to sit there in order for it to operate at the sort of fidelities and reliability that you need. What Vector Atomic has shown is that they can actually beat that box, do better than anything else out there besides these one-off labs, in deployed environments. They can take their 3U atomic, like rack-mountable atomic clock, and they can put it on a ship. They showed that they can put it on a ship, in a car, on a plane. They're working on putting these things on satellites in space, and we'll have the highest precision atomic clocks that can act under all different kinds of motion and environments. So that's really exciting. They also build these things called gravimeters. So gravimeters just try to track the effects of gravity, and they showed that they can deploy that on certain types of ships. And it's really interesting in like submarines or in GPS-denied environments, like military submarines, is you can't necessarily ping out from them, because if you try to communicate out of your submarine, the adversaries can immediately see you. So you have to really try to understand what your situational awareness is, where you are in the world, based on the technology you have housed in your submarine. Right? And what they do is they use like gravitational maps that we have. And so what we've done in this demonstration is that we showed with our gravimeters, we're actually getting really close to what the leading like gravitational maps are showing for like the subsurface of the ocean floor and that sort of thing. Okay, so we're deploying these things. The last thing is a gyroscope. We actually launched one of these to space. So what we're showing now is that we can ruggedize this technology. Getting through a rocket launch is very significant. It's not easy to do. A lot can go wrong. You have to do a lot of radiation controls and that sort of thing. We showed that we can actually ship this thing out to space. So what do we want to do from there? Well, we acquired a company called Capella Space that has a satellite constellation. They do something called synthetic aperture radar, which is effectively this wide area radar that allows them to scan the ground in low Earth orbit, and they can get situational awareness. They run AI. They can try to understand if things change across the globe. But what's unique about their radars versus others is they can actually see through trees. They can see through objects to the ground. So it's interesting, and like someone like military in Russia or some other country might be trying, they take advantage of the fact that most satellite imaging can't see these things. So they'll do things in forests, right? And now with this technology, we can see through that. So we want to connect all this technology together. That's the ultimate plan. So one of the first things that we might do is take those atomic clocks and put them in the satellite constellation. We put them all on that, so now we have the most precise timing and synchronization that we can get for the satellite constellation that's already doing this imaging, right? Then what we want to do is take these QKD boxes, put them on there. And we acquired a company called Skyloom that is leading in high frequency, or they're leading in optical communications between satellites, right? So really fast comms between satellites, and so what we want to do is connect all our satellites, secure them with QKD, secure communications with ground stations, connect them back to our computers, and have this wide area platform that we can start to explore spaces that just otherwise could not be explored. No one else can do this. This will be the first instance in the world of taking these leading technologies that they're not quantum just for the sake of being quantum. They're quantum because these technologies really are the leading technologies, and we want to have them deployed in all these major arenas. So we'll be satellites in space interacting with aircrafts in the sky. We're working with a company called Haven for drones, so we can do the same kind of optical links with them, maybe putting atomic clocks on fighter jets. On the ground, we'll have our quantum computers and building these large area networks for secure communications. And then, like I said earlier, we're even out at sea now with some of our sensing units. Okay. I'm doing okay on time. I think I can stop there. Thank you all so much.
I just want to quickly add, thank you so much, Dan and David at IonQ. What you guys just witnessed right now is a maiden talk. This talk has never been given before. If I'm not overhyping this, these slides were created specially for the Texas Quantum Economy Conference. I think they have spoken about this in bits and pieces. But this entire presentation put together today was just done here. So this is their maiden talk. This is the first time you've not seen this online. These slides have never been distributed. And we really thank Dan and David for working with us through this. The main requirement here was to talk to an audience that didn't come from this background. And I've heard a lot of questions, people asking, what are they being used for? What is a quantum computer? Well, our classical computers can do that. And there are lots of sources online. We hear a lot of podcasts, a lot of YouTube videos. But I thought it was time for the real source, IonQ, to talk about their technology in a way that everyone can understand so that it's not being misrepresented, it's not being interpreted. You are hearing this right from the experts that are actually building these systems. So thank you so much. Dan, that was an excellent talk. I think that talk belongs on a TED Talk show. Especially with your 5-year-old daughter being part of this. I think that was really, really precious and very, very well done. Thank you so much.